Hi everyone, and welcome to today's webinar, Educating Engineers or Training Technicians. My name is Donna Long, and I will be your host during today's webinar, presented by Zane Scott. Zane is the Vice President for Professional Services at Vitech Corporation. He is responsible for leading the delivery of training and consulting services, as well as the development of educational and intellectual collateral. A frequent blogger and speaker on systems engineering topics, Zane co-authored Vitech's primer for model-based systems engineering with David Long, Vitech's president and former NCOSE president. Active in the International Council on Systems Engineering, Zane is a co-chair of the Corporate Advisory Board and a member of the Board of Directors. He has delivered the SE 101 tutorial for the NCOSE International Symposium for 3 years, won a Best Paper Award with Dave Walden of Sysnovation at IS 2016, and teaches the fundamentals of systems engineering for Vitech at other companies and NCOSE chapters. Zane comes to the world of systems engineering with a diverse and interesting background, having been a trial lawyer, hostage crisis negotiator, labor management facilitator, and mediator. He is a member of the inaugural cohort of NCOSE's Institute for Technical Leadership and is particularly interested in developing leadership skills among engineers and other technical professionals. Before joining Vitech, Zane worked as a senior consultant and process analyst, assisting government and industry clients in implementing and managing organizational change. Before Zane gets started, I have a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitech's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome, Zane.
Thanks, Donna, and welcome everybody else. We're happy that you chose to spend some time with us this morning in a topic that I hope you'll find interesting and perhaps think about in some different ways by the time that we're finished. When we look at any discipline, we see that there are a set of concepts and then a set of skills or a set of processes that bring those concepts to life. The ability to think at the conceptual level is, I think, absolutely critical in terms of being able to see the ways in which those concepts can be applied to do things in the world, to actually help people, to make application. One of the ways that this finds expression is in the difference between education and training. And we're going to address that, but we're more importantly considering what's behind the difference between training and education. So let's talk about where we're going to go this morning. We're first going to talk about the conceptual framework. What do we mean by a conceptual framework for a discipline? And how does it help us to have such a framework? Then secondly, we're going to talk a little bit about the bias toward practicality, the bias toward application, and talk about that in the context of the difference between education and training. Any of those of us who engage in education or training find that there is a strong bias in our audience toward the particular application of the subjects that we talk about. I always laugh, we have a client who are engaged as an organization in the design of railroad systems. And so every time we work with them to talk about model-based systems engineering, they want everything to be cast in the framework of designing a railroad system. and they want all of their examples to come from there. They want to talk about the concepts in that application. And we as a society have a pretty strong bias toward the practicality, often to the detriment of the conceptual framework. And we'll talk about how that can result in some issues and problems for us along the way. We're going to talk about the history of the development of systems engineering, which has a very strong relationship toward our bias in the systems engineering world toward practicality and toward process, and how that has acted to limit us, and some of the barriers that have resulted from the way in which the discipline has developed and is developing, and actually where we stand today. And then I'll have some suggestions for a path forward and some things that I think we need to think about and be doing. So with that, let's get started. We're first going to talk about the conceptual framework. I chose to use an example of electrical engineering to talk about the difference between the conceptual framework and the process and practical application. I went to the United States Department of Labor Bureau of Labor Statistics for the definition of the job classification of electrical engineer and the job classification of an electrician, to look at how those differences are expressed. When you look at the electrical engineer, what you see is research, design, develop, test, or supervise the manufacturing and installation of electrical equipment, components, or systems for commercial, industrial, military, or scientific use. When you turn to the definition for an electrician, you find install, maintain, and repair electrical wiring, equipment, and fixtures. Ensure that work is in accordance with relevant codes. So you see the electrician's responsibilities are pointed directly at the practical application of what the electrical engineer is called upon to understand. So the electrician does not have research responsibilities or design responsibilities or development or test or even manufacture. They simply take what has been created for a particular use and go through prescribed processes in compliance with the relevant codes and install, maintain, and repair the wiring, the equipment, and the fixtures that are necessary to do that particular job. So if we look at the world of electrical engineering, we see that the electrical engineer is more concerned and is differentiated from the electrician by their concern with the concepts. And this is the classical way in which we would distinguish a discipline from its applications. So in a classical conception of a discipline, you would take the concepts of the discipline and apply them to particular situations, and that gives you your different applications. So with electrical engineering, you might have an application in terms of power generation and transmission, where you would be looking at generating electricity and transmitting it oftentimes over great distances and through a grid. Or you might have an application that involves building and creating particular equipment, or you might have an application that involves wiring a residential dwelling. So you would take the same electrical concepts and make applications in particular ways. The technicians would work at the application level, and the engineers work at the conceptual level. And this really gives us the difference between education and training. In the book Team of Teams that Stanley McChrystal and others have written, we find a discussion of the difference between education and training. They write, "We would never call the rigors of medical school easy, but it's more feasible to spend 7 years learning about the complex cause and effect relationships in the human body than to attempt to record and memorize every possible event that can befall bodies. This is the difference between education and training. Medical school is education. First aid is training. Education requires fundamental understanding, which can be used to grasp and respond to a nearly infinite variety of threats. Training involves singular actions, which are useful only against anticipated challenges. Education is resilient, but training is robust." What they're pointing out here is that education operates at the conceptual level and then applies the concepts to particular situations, whereas training trains you for particular situations. When we look at the classic dictionary definitions, we find that lived out as well. Education is the act of imparting or acquiring general knowledge, developing the powers of reasoning and judgment, whereas training would be the action of teaching a person a particular skill or type of behavior. So once again, you see from the dictionary definitions that it's a case of concepts versus particular skills, general knowledge versus specific situational knowledge. Now, we carry a bias within that comes out in lots of different places. I was actually surprised as I was researching for this presentation at the ways in which this bias leaped out. So I captured one of them to show you. A discussion of training by an institution that was selling training said, "Training gives you the skills to do something rather than just know about something." You see the bias there? It's do rather than just know. So an electrical engineer just knows about something, but an electrician can actually do something. And we have that strong bias. Probably there are some engineers out there squirming going, no, 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 I know how to do some things. And that's true insofar as our bias has pointed us toward training. But we have an intense desire to be practical. We want to acquire skills, and we want to acquire them as easily as possible with as little reference to the theoretical underpinnings as we can possibly get away with. So we want to learn to read music, we want to learn to play the piano, but we're not necessarily interested in the theory of the construction of chords, for example. And what this leads us to is to become technicians who practice our music in particular areas. I got a good lesson on this when I was in college. My parents moved to the area where I still live today, and we moved from the folk music of the late 60s and 70s, which is the way that I learned to play guitar, into an area where guitar players played bluegrass. I discovered quickly that I didn't need all those fancy chords that I had learned in order to play Simon and Garfunkel. I just needed 3 chords, and all I had to do was translate them from key to key. And if I didn't want to bother learning those 3 chords in a different key, I could just use a capo on the neck of the guitar. And so a bluegrass guitarist was practicing something entirely different than the finger-picking folk guitarist in the world from which I had come. Who's a better guitarist? That's a useless discussion. Each one has their separate skills, but it was good that I had had some music theory so that I could make some translations and transition between those two different applications relatively quickly. But the translation happened at the conceptual level rather than the practical skills level. So, how have we historically come to define systems engineering? We've come to define systems engineering in terms of process as opposed to concepts. When you look back at the history of defining the process, you find waterfall examples in one form or another, where we worked first in requirements, then in behavior, then in the physical architecture, then in verification and validation. But the waterfall method, so to speak, defines systems engineering where it's used and defines it in process terms. Now, there were problems with the process, so the process gets altered along the way and becomes a different process, rapid spiral development, for example, or the classic V model, which is related to processes behind it, but nonetheless talks about systems engineering in the context of a set of processes and process steps that we perform, as opposed to concepts that we know and make application of. One of the earliest definitions of systems engineering is the old mill standard 499, and that was the DoD's definition of systems engineering. That's a process definition. It talks about systems engineering as a set of processes. 499 went by the wayside when the Department of Defense decided to move to a commercial standard instead of a DoD manufactured standard. So EIA 632 came out in response to DoD's cancellation of mill standard 499. And when you look at 632, you realize that it's a process definition as well. It talks about the process. It's a good example, the transition to the commercial standard of 632 from the Department of Defense standard of 499 is interesting, because in moving to commercial, look at who was included and thought of as the commercial applications. DoD was in there for the history and for the current state of the mill standard, but it was the Aircraft Industry Association, the National Security Industries Association, the Institute of Electrical and Electronics Engineers, and INCOSE, which was made up mostly of folks from the industry areas that were already named there. In other words, DoD, in going commercial with their definition, not only stuck to process, EIA 632 not only stuck to process, but in addition to that, the process stayed defined in the context of military aerospace processes. So it was not as if we went out to the general economy to try to define process. We defined process, and we defined it in a narrow, highly tailored application drawn from the private practitioners of the old mill standard 499. IEEE 1220 in 1998 is pretty forthright in saying that it's a standard for application and management of systems engineering process. Once again, process definition. In other words, how we do it as opposed to what we do, or much less why we do it. So we've grown up with a process definition and a pretty narrow and highly tailored process. So systems engineering is thought of and conceived of in terms of the processes as opposed to the concepts behind systems engineering. To the extent that we understand concepts, they've largely been drawn from a set of applications, and the applications that have been made have been mostly centered around the highly tailored military aerospace processes that formed the early part of our history as a discipline or a practice. In some instances, we have made some translations into other areas, and we'll talk about that in just a minute. But this has created a set of problems for us. The problem comes when we try to look at what else we might do, when we realize that we're practicing a discipline whose major client periodically makes decisions like, okay, I'm going to take all the money and sequester it, or I'm going to come to a total halt with my budget because I don't like what's going on. And we're looking to diversify and to move to other areas to protect us from the vagaries of our traditional market space. And we find that when we try to move to other areas, others don't recognize our processes. When we get outside of the narrow context, the tailored military, aerospace, electronics, and software kinds of processes that we're used to, we find a world that doesn't really recognize our processes. So what are the hurdles that are created? What are the obstacles that we wind up facing as we do this? Well, the first hurdle has to do with language. We have lots of jargon, lots of acronyms and limitations, and we talk about the process. Not only is it a process that is structured in a very highly tailored way, but the names that are attached to the process steps and to the actions taken within the process are cast in a jargon that's opaque to people, and the further you get away from the kind of tailored application that we begin with, the less understandable the jargon becomes. There's also outright confusion. So you take a concept, for example, like failure mode effects analysis, FMEA. The meaning in ASQ and the Food and Drug Administration, the oil and gas industry, and DOD, where it's actually generally referred to as FMECA, can become entirely different. And concepts within it can get cast in different ways. So risk and reliability and concepts that are central to this area are understood in different ways in different areas and different industries. And our casting of systems engineering in one particular narrow way makes it difficult. And so once again, you have a mill standard here that was canceled so we could move to a commercial standard. But the commercial standard that we moved to doesn't look much different than the mill standard that we had before in terms of its language. There's out and out confusion, as I said, where the same term is used differently. I remember being confused when I came from a world where I thought I understood the word agnostic. And I began to hear software developers who would say things like, my program is operating system agnostic. And I would think, that's interesting. Agnostic comes from the Greek word gnosis, which means knowledge, and the application of the a prefix to knowledge means without. So, for instance, in the world of theology, an agnostic is somebody who doesn't know if there is a God. They have no knowledge of whether or not there is a God. So why would a software developer say that it's a good thing that their program has no clue as to what the operating system is? That didn't seem to me to be a selling point. And then I came to realize that what they meant was that the operating system, the program, didn't care what operating system was there. It could operate no matter what operating system was present, what the environment it was put into was. And so it didn't care about it. And there's a perfectly good Greek derivation for that. Caring or concern is pathos in Greek. And so not caring or not being concerned is to be apathetic, without feeling. So what they were really saying was that not that their program was operating system agnostic, they were saying that the operating system was apathetic. That was confusion because I'd been introduced to the word in another world and walked into a world in which it was used in a completely different way. So the communication broke down. Another way in which our history and the way that we've conceived of things limits us is that conceiving it in terms of highly tailored applications means that it becomes more difficult to see applications outside of the ones that we were engaged in. I remember giving a talk a number of years ago where I talked about this concept, and after the talk was over, one of the guys in the room came up and he said, your talk was really interesting and it really got me to thinking, we could diversify. We're producing tanks. We're using systems engineering to come up with tanks, and we could do bulldozers too. And I'm sitting there thinking, that's a real diversification. That's a great leap sideways to go from one tracked vehicle to another. And then what I realized was that he was recognizing the shift in terms of the application. So he looked for not a place where the concepts could be applied to solve a different kind of problem. He was looking for an application that looked familiar to the one that they had already been successful with. And so the application resulted in a narrowed context because we couldn't see beyond the application to the concepts. The way that limits us is that without a contextual vision, we have difficulty making a translation. So if we're building tanks and ships and planes, and we have our own jargon and our own language problems, and then we go and approach the administrator of a hospital to talk about designing a system of operating room procedures, we have trouble translating from one application to another because our view of our discipline is very highly tailored, and it's not going to be recognized by people who don't have that context themselves. So it creates a divide there and makes it difficult for us to transfer. So what we have essentially is, you remember, we've got concepts that are derived from applications instead of applications being derived from concepts. How does this hurt us? Well, one example is that we tend, because we don't know and understand the concepts, we can actually fail to look at them. NCOSE has come out with the Complex Systems Working Group has published a complexity primer, which is an excellent resource for somebody wanting to be introduced to the world of complex systems and complexity. And very early on in that complexity primer, they make this statement: the standard systems engineering process breaks down a problem into parts recursively until the parts are simple enough that we understand them and can design solutions. We then reassemble the parts to form the whole solution. Well, that's interesting because it violates the concept that sets us apart from other engineering disciplines. Because as systems thinkers, we're supposed to be following more along the track that Russell Ackoff lays out in the second quote. In systems thinking, increases in understanding are believed to be obtainable by expanding the system to be understood, not by reducing them to their elements. Understanding proceeds from the whole to the parts, not from the parts to the whole, as knowledge does. So our understanding is based on the use of principles that we can easily forget if we don't focus on at the conceptual level rather. As an example, dealing with complexity. Complexity is certainly part of the basic conceptual framework for systems engineering. And the complexity primer says, but busy systems engineers rarely have the time to keep up with the literature, meaning the literature of the other systems disciplines, which is diffused across the many interdisciplinary applications of complex system science. So the Complex Systems Working Group is recognizing here that most engineers focus on process and application rather than at the conceptual level. So, for instance, we don't necessarily understand the difference between detail and dynamic complexity. We have just the vaguest notion of the difference between physical and adaptive complexity and complex systems. All systems produce results not possible for any of their elements. And that's particularly problematic for complex systems because the prediction of the results is really the business of the engineer. We're designing a system to solve our clients' problems. And in order to do that, we have to be able to predict the results that will come from the design. And when we do a complex design, we need to be sure that there are not unintended deleterious effects that come from our design, but we also need to be sure that the results that we're looking for are manifested from the design. So we have to manage complexity, and we need to manage and maintain the desirable complexity, because that's where we get adaptability and resilience, and we need to understand that in the systems. But we have to be aware, and we have to raise our heads up out of the business of applying processes enough to do sufficient conceptual thinking to understand this. So what's our path forward? What kinds of things can we do to increase the quality of our discipline and to increase our understanding of it. The first thing is that we need to move toward a more natural language. Russell Ackoff said, unless people can express themselves well in ordinary language, they don't know what they're talking about. And that's very true, because in order to express ourselves in ordinary language, we have to understand the problem or the solution that we're talking about in conceptual terms and be able to express that. Actually, I need to point out here that his real quote says in ordinary English, but I altered that to say language, because I think it's equally true that in France, if you can't express yourself well in ordinary French, then you don't know what you're talking about. And so the understanding comes from being able to think in ordinary terms as opposed to technical jargon. We have some examples of attempts to do that. And I've got two examples here, and I put them up not because I'm advocating one or both of these examples, but because I think they show us the way in terms of the direction that we need to move in altering our language. The first one is from 1998, Bayhill and Gissing out of the Arizona. And here's how they state the systems engineering process. Now, you can see that you can translate this into the technical terms and the tailored terms that we use all the time. But they have used language that could be understood by anybody. So it could be as well understood by the engineer, by the research scientist, by the hospital administrator, by the organizational design specialist. We take those folks through stating the problem, investigating the alternatives, modeling the system, integrating, and then launching the system and assessing performance and reevaluating at every stage and rethinking. That's understandable as opposed to some of our more freighted and tailored descriptions. Another model comes from Cecilia Haskins from her PhD thesis. She talks about the Spade Model, where you have stakeholders, problems, alternatives, decision-making, and evaluation. And in her paper, she goes on and explains how you move through these elements and how you work with solving your problem, holding all of these in consideration. But again, any reasonably educated person can understand this and can understand the explanation that Cecilia applies to the Spade method. So what are we looking at in terms of our path forward? We're looking at taking the concepts first. We need to focus on the concepts. We need to focus on them as practitioners. For instance, we shouldn't forget that we understand systems by putting them together as a whole rather than deconstructing them and then aggregating them back into some sort of a cobbled together solution. And we need to understand it as educators. We need to understand as we teach young systems engineers that they need to learn the concepts. And what are the concepts? Well, the concepts come from systems thinking and complexity. That's the conceptual level, and it's not limited to that. There are certainly a number of concepts, but we don't do a good job of identifying what the overall concepts are, much less conveying them as educators. Now, this is not an indictment of educators across the board, because there are folks out there who are doing a good job of teaching their folks to think in conceptual terms. But by and large, as a discipline, we forget to do that. The next thing is we need to resist highly tailored standards. So if you attempt to impose a standard and the standard is highly tailored to a small portion of the audience that you're seeking to impose the standard on, you're going to have problems. This will date me a little bit, but I went to college with a slide rule. In my freshman year, the HP 35 scientific calculator from Hewlett-Packard became really, really popular. In 1972, it was taken into space by the astronauts, and then its popularity really took off. And Christmas of my freshman year, lots of the engineering and scientific technical students that lived around me at school came back from Christmas with HP 35s that they'd gotten as gifts. They were priced at $395, which in today's dollars is about $2,200. But the HP 35s used reverse Polish notation as an entry method. Now, when I use this example in speaking, it never fails. It may fail today because it's a little more difficult to get to me, but when I use this example with a live audience, I always get 2 or 3 people who come up and want to give me a lecture on the superiority of reverse Polish notation as a way to deal with math problems. But the market was not used to that way of notation. And so when TI later on during the year came out with the SR50 using the normal left to right algebraic type notation, they began to swallow up Hewlett-Packard's market space. And we were off to the races. So the SR50 used a standard way of entering the terms of the problem that was more in consonance and better recognized by the marketplace. So I think we have to be careful in attempting to impose standards that come from a highly tailored environment. Our military processes, our different reports, our tailoring is not going to be recognized by hospital administrators who largely, to the extent that they think about process re-engineering, are coming from the world of TQM and its progeny, Lean Six Sigma. So software standards, likewise, are not going to work for NGO leaders fighting infectious disease outbreaks. But hospital administrators doing process re-engineering and NGO leaders trying to design a system to apply the resources where they're needed, when they're needed in order to curb infectious disease outbreaks are folks that need systems engineering. And they're folks that systems engineers can very well help. But we can't do it by attempting to impose on them, say, the documentation standards from the software world for modeling. So when we talk to them about modeling, we can't do that in terms of highly tailored standards and terms. So where have we been? Well, we've talked about the fact that systems engineering developed largely in a pretty specific market segment, and that has impacted the way in which we look at systems engineering. It was defined in terms of processes. So it was defined in terms of what we do rather than how we do it, or most of all, rather than why we do it. The processes that were defined were highly tailored, and largely limited to the specific market segment. We've made some moves to move into other areas, but they tend to be lateral steps that are very small. Our language wound up being tailored as well, and so we have lots of jargon. We use words in ways that are specific to our arena that are not necessarily understood in the same way outside of the world of systems engineering. And all of that mounts up to mean that our transferability to other domains is made more difficult. We need to learn to see systems engineering at the conceptual level. And we need to learn to speak about it in a language or languages that others can understand. The goal is communication. We tend to look at it as if the goal is evangelism. We need to convert the world to our particular way of thinking or seeing. So we become advocates for SysML, we become advocates for particular ways of doing things, advocates for particular processes. And the goal is communication. So we need to open ourselves up to learn to communicate in ways that can speak to as broad a marketplace as possible, so that we can really carry out the kinds of things that the NCOSE Vision 2025 talks about when it talks about systems engineering as a way to solve large social problems, for instance. We need to tailor our solutions to the needs and not try to tailor the needs to the solution. So we don't need to take a pre-tailored solution into a setting and attempt to help the people in that setting by tailoring their need back to our solution. It needs to work the other way around. We need to take the concepts to the particular setting and tailor our solution to respond to the needs of the people in that setting. I think that would give us a way of translating the concepts of systems engineering into the ability to help and to solve problems for a broad range of people. And in terms of economics for us as systems engineers, I think it opens up a market space that allows us to be much more successful and much less servants to a particular narrow space. And with that, I am ready to take questions.
Thanks, Zane. We do have a few questions, thanks to our participants. I encourage you to join the discussion now and submit your questions using your webinar control panel. Our first question is from Jamie. How do we go about moving to a conceptual view when all of our experience is application-based?
I think that's the essential trick. And I think one of the ways to do that is to look at some of the work that's been done. If you go to the NCOSE site and look back at papers that are there in the publications library, which we all have access to as NCOSE members, you'll see that there's been some interesting work done on the relationship of systems engineering and the other systems disciplines. Henry Silito is a name that leaps to mind as having done some good work in that area. But I think we have to learn to be interested and inquisitive and to branch out and look at people in other areas. Fritjof Capra and his 2014 book, A Systems View of Life, would be a good place to start. And think about that in terms of the applications that we're familiar with as we read about a more general application of those principles. But it's a matter of curiosity and a matter of some effort, but I don't think it's undoable for any of us.
Okay. Our next question is from Brian. He asks, engineers want to build systems. How do we communicate the need to evaluate the concepts before trying to build a solution?
And again, I think that's part of the essence of what we're talking about here. In terms of communicating the need, we're the audience that needs that communication, because that's a step that we tend to skip. And until we convert ourselves to the need to do that, it's going to be difficult for us to convert our customers or the world around us to that. So I think as my mother used to say, good manners begin at home. I think that conversion begins at home.
Okay. One more question from Dana. What do you think all this means for systems engineering education?
I think the basic thing that it means is that systems engineering needs to step up and take its rightful place in terms of having the dignity of being an outright engineering discipline. I don't think that we need to take a back seat and to simply confine it to graduate schools or certificate programs or as an adjunct skill taught to other better educated folks. I think we need to seriously look at the conceptual framework. I think we need to develop that, flesh that out, and I think that we need to get to the point where the typical systems engineer comes up as a BS, MS, PhD person rather than somebody who jumped on the bandwagon later in their career or later in their academic studies.
Okay, and we just had one pop in here. It's from E. Walker. Zane, I saw several of your slides that portrayed SE in medicine. Do you have any examples of healthcare companies or institutions that have adopted or embraced the SE approach mindset?
I don't have any that spring to mind right now, although I know there's some work that's being done. It's really interesting, and the reason that I use that as an example is that when NCOSE decided to move into the healthcare world, the first move was toward medical devices. And that's logical, but that's a move that's designed based on asking ourselves what applications look the most like the applications we're currently making. So we'll go bend metal and hook up wires and build devices, where the biggest problems in the healthcare world are not in terms of the innovation and engineering around medical devices, but they're in the systems that actually deliver the care. How do we deliver high quality care? How do we deliver preventive medicine? Those sorts of things. I think there's some people within the healthcare working group who are talking about the process side. And I think there's some work that's going on, but mostly in the context of Lean Six Sigma, process improvement, total quality management. In other words, ASQ has a bigger share of that than NCOSE does.
Okay. Zane, that wraps up our Q&A for today's presentation. If you have any other questions or comments for Zane, please don't hesitate to send him an email. His address is on the screen. He would be happy to hear from you with any inquiries you may have. Thanks for coming today. Our next webinar will be Failure Modes Effects Analysis in Model-Based Systems Engineering with Ron Kratzky. The link to register is on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. That's all for today. Once again, thank you for joining us and have a wonderful day.